Okay. These are the topics for today's class. Before I present the topics, let me show you some statistics about exam 2. In exam 2, how many people participate in exam 2? Let me see. 21. The average of exam 2. The average of exam 2 is 81.57. The top score is 89.5. How many people receive 90 or above? Number of 90 or above. How many? Let me see. 6 people. 6. The median. The student whose score is in the middle is 85.8. Again, I will put your exams in an envelope on the door of my office, so that you can go to my office to pick up your exam. Okay. This is about exam 2. Overall, the performance is very good. It's very good. Okay. Now today's topics. The first topic, how to find all the eigenvalues of a matrix, square matrix. Okay. For eigenvalues, we only consider square matrices. The second topic, similar matrices. And the third topic, diagonalize a matrix. Now, take a review first about what is an eigenvalue, what is an eigenvector. Take a review. Okay. Number 8. If a non-zero vector V and a scalar lambda, this scalar can be 0, can be non-zero, satisfy this equation. A times V is equal to lambda times V. Whenever a non-zero vector and a scalar satisfy this equation, we say that V is an eigenvector, and the scalar and lambda, the scalar, corresponding or associated eigenvalue. To check whether or not a vector or a scalar are eigenvectors and eigenvalues, check this equation. Whenever this equation is true, then the non-zero vector is eigenvector and lambda an eigenvalue. Okay. So this is the definition of eigenvalues and eigenvectors. Second, B, take a review. What B is? Let A be a square matrix. Say the size is n by n. And suppose lambda is an eigenvalue. Of the matrix A. An eigenvalue has infinitely many eigenvectors corresponding to it. Now I put all the eigenvectors together. I have a set. The set of all eigenvectors corresponding to the eigenvalue lambda. Below that, eigenvectors are non-zero vectors. So plus the zero vector. Okay, put all the eigenvectors together, and then also put 0. Then together we have a set. This set is called the eigenspace. Eigenspace of matrix A corresponding to the eigenvalue lambda. The eigenvalue lambda. Okay. So how to find eigenspace? We know that eigenvector satisfy this equation, right? To find eigenspace, to find this set, solve this equation, right? Solve this equation. Then the non-zero solution is an eigenvector. But this equation, I can rewrite it as move the right side to the left side. Then the right side is a zero vector. Move the vector on the right side to the left side. Then right side is a zero vector. Then take out x. But before I take out x, don't forget, put an identity matrix. Because a matrix minus a scalar not computable. So now take out. So this equation actually is this equation. Solve this equation for all the solutions. Each solution is an eigenvector. So therefore, the eigenspace, the set of all the eigenvalues, all the eigenvectors plus 0. The eigenspace is the null space of this matrix. Null space. Recall that what is the null space of a matrix? Null space of a matrix M. It is the set of all the solutions of this equation. The set of all the solutions of this equation is null space of the matrix M. Yeah, the solution clearly includes 0, right? When x is 0, it is a solution. So eigenspace is no space of this matrix Yeah, this is the review, okay, about some key points from the last class. Now, today's topic 1, how to find all the eigenvalues of a matrix. Topic 1, how to find all the eigenvalues of a matrix. The answer is based on the following observation. Okay, observation. The answer is based on this observation. Okay, number 8, observations. Yeah, 2 observations. Number 8. If lambda 0, it is a scalar, is an eigenvalue of a matrix A, then by definition, there is a non-zero vector such that this equation is true, okay, where V non-zero. Then I move the right side to the left side. This is a lambda 0, okay. Lambda 0 is an eigenvalue. That means that we can find some non-zero vector V so that this equation is true. Now I move the right side to the left side. To the left side. Then I have this equation. Now, factor out V. Before I factor out V, the second term, I write it as lambda 0 times identity matrix times V. Now, factor out. Yeah. Right. Now, from this equation, we conclude that the matrix A minus lambda 0 times I is not invertible. Why? Because if this guy is invertible, I can move it to the right side. Then I get V is a 0 vector, a contradiction to this assumption. So this matrix must be not invertible. Okay, this matrix is not invertible. Therefore, determinant of this matrix is 0. So therefore, this observation says that if a scalar is an eigenvalue, then this determinant is 0. Determinant is a number. This number determines whether a matrix is invertible. Now, 0. Okay. Now, second observation. Okay. Reversely, if a scalar lambda 0 such that determinant of this matrix is 0. Okay, if some scalar such that determinant of this matrix is 0, then below A minus lambda 0 is not invertible. In other terms, singular is singular. Singular means the matrix not invertible. When a matrix is not invertible, then this linear system has non-zero solutions. This is by part 4 of the invertible matrix theorem in section 2.3 of in my notes. It is a theorem 14.1 in section 2.3. This theorem is a list of the properties of an invertible matrix. Yeah, by part 4. Yeah. Okay. Now, when this equation has non-zero solution, then non-zero solution, then we have, okay, now let me multiply out this product. Then we have this. X is non-zero. Okay, so from here we have this equation. For a non-zero vector, whenever we have this equation, the vector, eigenvector, the corresponding scalar eigenvalue. So therefore, this implies that lambda 0 is an eigenvalue. Now, let me, based on these two observations, we have the following conclusion. Okay, conclusion. Okay, yeah, here. Conclusion. Conclusion. Okay, a scalar, say lambda 0, is an eigenvalue of some matrix A if and only if determinant of A minus lambda 0 times I is equal to 0. Based on the two observations, then we have this conclusion. Okay. Okay, now I am ready to find out all the eigenvalues of matrix based on this conclusion. Okay, first, let me make a remark. The determinant which determinant? This determinant A minus lambda I. After you expand this determinant, after this determinant is expanded by how to expand the determinant by cofactor formula, right? Expand determinant by cofactor, by the cofactor expansion formula. Expansion formula. Formulas. Okay. This is in chapter 3. Now we are in chapter 5. After we expand this determinant, then we will see that it is a polynomial in lambda of degree n. Suppose that A is n by n. I will show you examples why this determinant is a polynomial of degree n. I will show you examples. Okay, now, before I present how to find out all the eigenvalues of a matrix, let me present a definition first. Okay. This remark says that this is a polynomial. Okay. The polynomial determinant. Okay, determinant. A second notation is I can put a vertical a pair of vertical lines on the both sides. This is a determinant. The determinant, we give a name to it. It's called the characteristic polynomial of matrix A. Just a term, just a term. Okay. B, the equation. Yeah, set determinant to 0. The equation is called, also give a name to this equation. The characteristic equation of A. Okay, now I am ready to answer the question how to find all the eigenvalues of a matrix. It is a field. Okay. A scalar lambda 0 is an eigenvalue if and only if from the conclusion here, a scalar is an eigenvalue of a matrix if and only if this determinant is 0. The determinant is a polynomial. So based on the conclusion, a scalar is an eigenvalue if and only if the scalar is a root of the characteristic polynomial is this equation. Yeah. Conclusion is lambda 0 is eigenvalue. Then we have this equation. This equation is true. Determinant is equal to 0. In other words, lambda 0 is a root of this equation. Left side polynomial. Lambda 0 is a root of polynomial. A root means polynomial make the polynomial 0. That is called a root. Okay. All right. Now, therefore, because of this field, therefore, to find all the eigenvalues of a matrix, we solve this equation. We find all the root of this equation. So give me a matrix. How to find all the eigenvalues? Compute this determinant. Then set this determinant to 0. Then find all the roots of this equation. That are all the eigenvalues. Okay. Let me show you examples. Okay. Take a look. Example. Example 1. Let A be this matrix 2 by 2 matrix. Now questions. A. Find the characteristic polynomial of this matrix. This example has 3 questions. Let me answer this question first. Characteristic polynomial. What is that? If you don't remember, go back to the definition. Yeah, where? Definition here. What is characteristic polynomial? This determinant is characteristic polynomial. Okay, now let me compute this determinant. Now compute A minus lambda I determinant. What is A? 2, 3, 3, 6. Minus lambda, what is I? This is I, then determinant. Okay. A matrix minus a scalar times a matrix. It is 2 minus lambda, right? 2 minus lambda times 1 is this. 3 minus lambda times 0. So number 3. 3 minus lambda times 0. Number 3. Negative 6 minus lambda times 1. Determinant. How to compute this 2 by 2 determinant? We have a formula for a 2 by 2 determinant. It is the product of the diagonal entries minus product of anti-diagonal entries. Now, let me simplify this polynomial. It is a polynomial of degree 2. Okay, let me simplify. Okay, distribution. Then simplify the expression. Cancel out something, right? And then combine some terms. Then we get this polynomial. This polynomial is the characteristic polynomial of this matrix. This is a question A. Now, question B. Question B. B. Find the characteristic equation of matrix A. I don't remember what is the characteristic equation of matrix A. Now go back to definition. Let me see. Characteristic polynomial, set it to 0. This equation is characteristic equation. Okay, now the answer is I found characteristic polynomial in pi here, so I set it to 0. Lambda squared plus 4 lambda minus 21 is 0. This is the answer. Okay, now question C. Find all the eigenvalues of matrix A. A polynomial of degree n has n roots. So a matrix of size n by n has n eigenvalues. Now n is 2, so this equation has 2 roots. Let me find the root of this equation. Okay, solve. How to solve it? 2 ways: by factorization or by characteristic formula. Okay, by characteristic formula, quadratic formula. Yeah, it is negative b plus minus b squared minus 4ac, then over 2a. Now quadratic formula. Now b is 4. 4 squared. Let me see. 4 times a. A is 1, right? The coefficient of the leading term is 1. Then times c, negative 21. Then 2 times a. A is 1. Then calculator. I get 3, negative 7. So therefore, all the eigenvalues of matrix A. Okay, the eigenvalues of the given matrix are these 2 numbers, 3 and negative 7. Okay, negative 7. Done. Done. Example 2. Second example. Example 2. Continue with example 1. Find all the eigenvectors associated with the eigenvalue. This is a continuation of the previous example. The previous example, we have 2 eigenvalues, 3 and 7. Okay, now find all the eigenvectors associated with, say, eigenvalue 3. Okay, of the matrix A in example number 1. Okay, now how to answer this question? Solution. To find eigenvectors, recall the definition of eigenvector. Okay, we need to solve this equation. Okay, Ax is equal to eigenvalue number 3 times x. Solve this equation. All the non-zero solutions are eigenvectors. Okay, associated with 3. Okay. Now, how to solve this equation? Again, move the right side to the left side. Then the right side is 0. Okay, now factor out x. Remember, before factor out x, write the equation by inserting identity matrix I. Now factor. Yeah. This is a linear system. Okay. To find the solutions, let me compute the coefficient matrix first. Okay. The matrix A in example 1, it is 2, 3, 3, negative 6, minus number 3 times identity matrix. Okay. So this is a 2 minus 3 times 1, negative 1. 3 times negative 3 times 0, number 3. And also number 3, negative 6 minus 3 times 1, negative 9. Yeah. coefficient matrix. So this linear system is -1, 3, 3, -9. And then the unknown is x1, x2. The right side is 0, 0. How to solve this linear system? Augmented matrix. Augmented matrix. Okay. So augmented matrix. The augmented matrix is right side 0, 0. Reduce the augmented matrix to the reduced epsilon form, right? Positive 3 times first row add to the second row. 0. Positive 3 times first row times 3, 9. Add to -9, 0, 0. And then scale the first row by multiplying it by -1. Then I get +1, -3. Yeah. 1, -3. Yeah. This is the reduced epsilon form. Now write the reduced epsilon form in equations. Right. In equations. The first row, it is 1 times x1 plus -3 times x2. x2 is a free variable. Yeah, first equation. Second equation, 0 is equal to 0. Okay, now the general solution. General solution means all the solutions. Solve for basic variable, only one basic variable, x1, in terms of the free variable. And then x2, arbitrary, okay? These are all the solutions. And also eigenvectors. But eigenvectors, an eigenvector is a vector. So write the solution in vector, okay? In vector. In vectors, okay? The solution is this, x, x1, x2. Now, plug in the first equation in x1. Then take out x2. Yeah, these are all the eigenvalues associated with the eigenvalue number 3. X arbitrary. So because x arbitrary, the eigenvalue 3 has infinitely many eigenvectors. Okay, the eigenspace. The eigenspace associate or corresponding to the eigenvalue number 3 is, recall that eigenspace is the set of all the eigenvectors, plus 0. So eigenspace actually is the set spanned by this vector. Span means all the set of all possible linear combinations. So eigenspace is the set spanned by these vectors. This vector is called a basis. Its basis is this vector. Yeah. The basis is this vector. Yeah. let me put this is into a set. Okay, yeah, this is a set notation. Yeah, the set of this single vector is a basis for the eigenspace, because the basis has only one element. So the dimension of this eigenspace, each space has a basis. The number of the basis is the dimension, okay, of the eigenspace is one dimensional space. Okay, done. This is example number 2. Now more examples. Example number 3. Then let me make the matrix size larger, a little bit larger this time. Okay. It is 3 by 3 this time. Okay. 6, -2, 0. -2, 9, 0. 5, 8. Number 3. Now the question is, find all the eigenvalues of this matrix. It is a 3 by 3 matrix. Therefore, this matrix has 3 eigenvalues. Okay. All right. Now, solution. How to find all the eigenvalues? Yeah. This figure. Yeah. Yeah. Here. To find all the eigenvalues, we find all the roots of the characteristic equation. Okay, now let me compute this part first. Characteristic polynomial. Okay. Compute the characteristic polynomial a minus lambda times I determinant. So 6 this is a matrix A minus lambda times I 3 by 3 identity matrix. Then determinant. Okay. So it is 6 minus lambda times 1. 6 minus lambda. -2 minus lambda times 0. -2. Similarly, 0. 9 minus lambda. 0. 5, 8. 3 minus lambda. Okay. Determinant. It is a polynomial. How do you see? Expand this determinant by cofactor expansion. Let me see. Let me pick the third column, because the third column has most zeros. Save my work. I expand this determinant across the third column. So the third column, this entry is A13. A13 times C13 by formula. A23 times C23. And then A33 times C33. Okay, now A13, 0. This is a 0. How about this guy? 3 minus lambda. So therefore, we have 3 minus lambda times C33. What is C33? we have a formula for C3 free. Negative 1 to 3 plus 3. Determinant of capital A, free. Capital A is a matrix. Okay. All right, now let me continue my solution here. Solution here. Here, solution. Then we have 3 minus lambda, negative 1 to the 6, positive 1. So, now capital A. Remember what is capital A from the original matrix by deleting row free, column free. Then this is a A3 free. So this is a 3 minus lambda. Determinant 6 minus lambda, negative 2. Then 2, 9 minus lambda, determinant. Okay. Now 2 by 2 determinant, easy to get it. It is product of the main diagonal entries minus product of anti-diagonal entries. Okay. Now simplify. Don't simplify. Okay. Here, I only simplify this part. I get this. And then factor out this because I'm looking for eigenvalues. Factorization, then I get lambda minus 5, lambda minus 10. Yeah, this is a characteristic polynomial. Now, how to find all the eigenvalues? All the eigenvalues are the root of this equation. That means that the numbers make this equation true. Okay. Therefore, eigenvalues make this polynomial 0. Number 3. Number 3 make this guy 0. 5 and 10. So 3, 5, 10 are all the eigenvalues of this matrix. Done. Finish. Done. More examples. Example 4. Example 4. Continue to make the size of a matrix larger. Find all the eigenvalues of this matrix. 5, negative 2, 6, negative 1, 4 by 4. 0, 3, negative 8, 0, 0, 0, 5, 4, 0, 0, 0, 1. Okay? This matrix has some special structure. Actually, you see, main diagonal line. Below main diagonal line, all the entries are zeros. So we call this matrix an upper triangular matrix. How to find all the eigenvalues of this upper triangular matrix? Find characteristic polynomials first. Okay. Solution. Compare A minus lambda times I, determinant, characteristic polynomial. Then this is a 5 minus lambda, negative 2, 6, negative 1, 0, 3 minus lambda, 0, 0, 0, 5 minus lambda, 4, 0, 0, 0, 1 minus lambda. Yeah. It's a matrix minus lambda times identity matrix is this. Now determinant. How to find this determinant? Recall that in the section about a determinant, there is a field. Determinant of a triangular matrix is just the product of the main diagonal entries. So this determinant is the product of the main diagonal entries. It is a 5 minus lambda times 3 minus lambda. 5, 1 minus lambda. Yeah. When you expand this product, you will see it is a polynomial of degree 4. Degree 4. Okay. Now I don't expand it. Okay. I don't multiply out the product because I'm looking for eigenvalues. Eigenvalues are the root of this polynomial. Okay. Now, from this polynomial, I can tell the root. What numbers make the polynomial 0? The eigenvalues. 5. Right? Plug in 5 here, then the product is 0. Number 3. Plug in number 3, the product is 0. And then plug in number 5 again here. Plug in number 1. So 4x4 matrix has 4 eigenvalues. These are the 4 eigenvalues. From this result, we can see that number 5, this eigenvalue is repeated twice. So we say that the eigenvalue number 5 has multiplicity 2 because eigenvalue 5 is repeated twice. 5 has multiplicity 2. How about number 3? Number 3 has multiplicity 1. And also eigenvalue 1 has multiplicity 1. Yeah, done. Triangular matrix, its eigenvalues are easy to find. Eigenvalues, just the main diagonal entries for triangular matrix. Yeah, let me put this into a field. Okay. Field. Okay. The eigenvalues of a triangular, upper triangular or lower triangular, it doesn't matter. Are easy. Are the entries on its main diagonal. Yeah. Okay. Before I turn to topic 2, let me point out the following common mistake. Okay, this is a common mistake. I saw some students make this mistake before. Okay, some people some people find the eigenvalues of a matrix A in the way, in the following way. How? Reduce A to epsilon form. Say, let me give a name to the epsilon form, say B. Okay. Epsilon form is a triangular matrix. Then they claim that the diagonal entries of the epsilon form are the eigenvalues of the original A, but that is wrong. Okay. Then the main diagonal entries of B are the eigenvalues of original matrix A, but is such a solution completely wrong? Okay. The problem is what is the problem? The problem is the eigenvalues of A and B, right? Reduce A to epsilon form. Then the epsilon form, its eigenvalues are different from the eigenvalues of the original matrix. Are different. So don't find all the eigenvalues of a matrix in this way. Okay. Yeah. This is a warning. How to find all the eigenvalues of a matrix? Compute characteristic polynomial and then set the polynomial to 0 and solve the equation. Okay. All the solutions of the equation are the eigenvalues of A. Okay. Don't by reducing A to epsilon form. Okay. Yeah. Common mistake. Yeah. Common mistake. Okay, now second topic. Let me see second topic. Similar matrices. Okay. Topic 2. Topic number 2. Okay. What is similar? Okay. Definition. Okay. Mathematics. Okay. Definitions and fields. Definition. Right. And then A and B, of course, square matrices and have the same size. B, 2 n by n matrices. Then we call these two matrices they are similar, not exact, but similar. If you can find there is an invertible matrix P, of course, the same size, okay, same size, such that A is equal to P times B times P inverse. Then we say that A and B are similar. They are not equal. They are not exactly the same, but similar. Okay. If you can find some invertible matrix P so that this equation is true, then A, B are similar. Similar matrices have many similar properties. Let me show you two similar properties. For example, number A, they have the same determinant. How to see? They have the same determinant. Yeah, here. Yeah, A and B are similar. That means that this equation is true. Now let me take determinant. Okay. One is A. A is P, B, P inverse determinant. Yeah, recall. I told you two basic properties about determinant. Do you remember that? A matrix times a second matrix determinant is equal to A determinant times B determinant. This number is equal to this number times this number. Second basic property is A take transpose, then determinant. It turns out that it's equal to A determinant. Take transpose doesn't change the value of determinant. Okay, now let me use property A. A product then determinant is equal to the product of determinants. Remember, determinant is a number. So this number times this number times this number, I can move this number here. But this number times this number by property A. P times B inverse determinant B. But P times P inverse is identity matrix. Identity matrix is you can view identity matrix as a triangular matrix. Determinant of a triangular matrix is the product of the main diagonal entries. So determinant of identity matrix is 1, so equal to B. So therefore, when A and B has this equation, A and B, they have the same determinant. Okay. Similar, A. Okay, now B. Second example, B. Similar matrices, they have the same characteristic polynomial, because they have the same characteristic polynomials. The roots of characteristic polynomial are eigenvalues. So therefore, they have the same eigenvalues. But a warning, but not the same eigenvectors. Yeah. These two matrices are only similar, not exactly the same. They have the same eigenvalues, but not the same eigenvectors. Okay. How to see they have the same eigenvalues, or they have the same characteristic polynomials. Compare characteristic polynomials. Compare. Okay. What is A? A and B is related by this equation. Okay. Yeah. So this is a P D P inverse minus I. Now, let me write identity matrix as lambda P times I times P inverse, right? You agree? Yeah, P times I times P. P times I is P. P times I is P. P times P inverse is I. So I can write I as P inverse. Okay, now let me take out common factor. Take it out. Common factor, take it out. Okay. Remember, matrix multiplication is not commutable. So B minus lambda I. Okay. P inverse. Okay. Yeah. So take this guy out on the right side. Okay. Here. Don't put P inverse here. Don't put P inverse here. They are not equal. Okay. Okay. Now, determinant of a product is product of determinants. But similar to here. Okay. So this number times this number is equal to 1. So therefore, we have, yeah. This is the characteristic polynomial of A. This is the characteristic polynomial of B. They are equal. So therefore, similar matrices have the same characteristic polynomials. Because the roots of characteristic polynomial are eigenvalues. So therefore, they have the same eigenvalues. Yeah. This is topic 2. Okay. Topic 2. Now topic 3. This is section 3. Diagonalize a matrix. What it means. Definition. Okay. Yeah. Topic 3. Topic number 3. Okay. Hey. Definition. Let A be an n by n matrix if A is similar to a diagonal matrix. Let me denote the matrix D, diagonal. Okay. What is diagonal matrix? Say for example, 1, 2, 3, 4, and zeros elsewhere. This is a diagonal matrix. Identity matrix is a diagonal matrix. Okay. If matrix A is similar to a diagonal matrix, then A is said to be diagonal. diagonalizable. Okay. In other words, we can diagonal matrix A. Okay. And more precisely, in other words, if you can find an invertible matrix P and a diagonal matrix D, so that such that A is P, D, P inverse, then A is diagonalizable. Yeah. We can, if you can find P and a diagonal matrix D, so that this equation is true. When this equation is true, A is similar to D. If you cannot find P and D, so that this equation is true, otherwise, A is not diagonalizable. Yeah, this is definition. Okay, so in the next class, okay, I show you more detail. Okay, I show you the details about diagonalizable matrices. Okay, and also examples in the next class. Let me stop here.